I think it's a great idea to start a series, where we can, go under the hood of LLM and see how LLMs are really created. And from there, we can either take it, like if you are a developer or builder of LLMs, you can understand those parameters and can fine tune and optimize them for your organization. If you are, cybersecurity professional, then you will probably take it further and do some research on LLMs and how can LLMs be used, how can LLMs be even hacked, right? How can you do fuzzing on LLMs, finding vulnerabilities in LLMs and so on, right? So there are a lot of interesting things we can do once we know how does something works under the hood. Okay. For those who have just joined, I think there is a yes. Hi, Ram. Yeah, please go ahead, Ram. You have any question to start? Great. I think we have one question already. Ram, if you can speak, go ahead. Okay. Maybe he's on mute. Ram, you are on mute, I think, if you're speaking. Uh, all right. So, in order to, make this session more fruitful, what I will like to do is you to do is also, go and create an account on Kaggle if you don't have it, and open this notebook. Okay. As it is a hands-on, we will have some hands-on session too, maybe towards the end. First, I'll cover the theory part, and then we will go to hands-on session, whoever wants to do it. And there will be a lot of interesting things when you do it. And what you can do is click on this link. You will get something like this and copy and paste. So copy and edit. Now, you may not have an account on Kaggle, so you may have to kind of sign up, do a sign in via Google, and you should be able to get an account. So once you copy and edit, you will probably get some, a notebook, something like this. Okay. So in the meantime, we are going through few things. You can quickly do it. Yeah. And if you face any challenge, let me know. We will try to resolve. All right. So let's get started. Any questions? Let me know. Okay. So our journey of, building a foundation LLM. By the way, thanks for coming. We'll start we'll go through in these phases. First, we will, in few sessions, we will cover like building the base of the model, right? Building some of the base components of the model, which includes, data preparation. We will also go through attention mechanism, which is the heart of, I think, LLMs, which has changed everything in 2008, 2016, I think, right? When the paper was suggested, attention is what you need or what you seek, and that has changed the whole industry. I think the author did not know that the paper is will be so valuable. Okay. So we'll go through in detail, in attention mechanism, in not in this class, maybe in later class. First, I think this class we will work on data preparation, and this is also extremely important. I'll explain you in a moment why. Okay, once we create attention mechanism, I think we will then go through the building other pieces of LLM architecture, okay, which include, layers of encoder and decoder. Then we will go through training it on a small data set, okay. It will be a really small data set. Of course, training LLM on large data sets is out of question. I mean, it requires a lot of GPU investments, but some of you who wants to build a LLM from scratch, I think you are most welcome. Okay, then we will also go through evaluating how to evaluate and load and pre-train, weights, how to load the model's pre-trained weights. Right? When we say pre-trained means it is the base foundation model, and from there now then you can start doing fine tuning and even building apps and assistants on it. Right? So I think this series we will focus on this base model, and also on building foundation models, which lead the path to our fine tuning, maybe in our subsequent sections, right? And you are here right now. Today we are starting, so great. Uh, have you? I hope you are already creating. You have already got access to the notebook. Maybe just say, just gives you a thumbs up. There is a, I think there is a way that you can show whether it is done. I think it will be, yeah. So look, something like this. Yeah, this is great. You have done it. Yeah, yeah, something like this you can do. Uh, there is a place just below, send a reaction, just below uh, share option in Google Meet. Yeah, great, wonderful. I think 2 or 3 people have already done it. Great. Okay, so before we dive into LLMs and history of LLMs, how to develop LLMs, let's ask few basic questions. So when we started working on LLMs, the LLMs were costing us a huge amount of money. Of course, they are getting cheaper day by day. I think they're also following Moore's law. Currently, GPT 3.5, like is an API, current GPT is 4.0, but GPT 3.5 was like 1 year back, which is also quite powerful model. It cost us $0.8 per million tokens input output, right? So what do you think? Is it more expensive or less expensive? What can you do with it? Any idea? Probably no, right? So before, getting to know whether this is very expensive, less expensive, I think it's good to know what is a token, like how to translate words and sentences that we know into tokens, and then only we can kind of estimate whether it is good or bad, right? So I think this session will give you enough understanding to know the difference, to know to even interpret this result of $0.8 per million kind of thing. Okay. Secondly, when you go to LLMs, all LLMs talk about context length. Like currently, the Llama 3, which is recently released by Meta, has a context length of 8K, 8,000. I mean, 2 bytes, 1 byte, right? And 8 kilobytes. Sorry, 8 kilobytes. And so, what does it mean? Okay. Now, Google claim that their Gemini has a context length of 100K to even 1 million. People are talking about 1 million context length. So what does it mean? I think that we get to know the answer in this section, in this tutorial. Every LLM supports a parameter called max tokens while generating text. What does it mean? Okay. Similarly, how can you optimize cost while utilizing LLMs? I think for that, if we understand tokenization, which is the uh, topic of this workshop, then I think you should be able to get a lot of ideas from it. Okay. Then I'm sure you're hearing about a lot of indic LLMs, the LLMs which are created on Indian languages such as Tamil, Telugu, and so on. So what do you think how do they really differ from other, like if you compare ChatGPT, Llama versus these Indianized LLMs? How are they really created? Do they need to create it from scratch? And if they need to create it from scratch, how will their training will differ from each other? In fact, you will be surprised that most of the language models that we see today, the only difference part is tokenization. Okay, and other things remains more or less very same. Okay, which is even very same to even the first paper which was released in 2016. So the architecture is almost same. Only thing which changes is tokenization. And this is what we are going to learn in this session, right? So you're going to learn how to create your own model. Just if you learn this session, this chapter, you're going to learn how to create your own model, like right, for any other use case from scratch. Any questions? So exciting. I think today is a very important part of this journey. The primary reason being, that this is uh, this is going to tokenization is actually definitely is the heart of. So how many of you are all set on the Kaggle notebook side, I believe? Just let me know. Okay. Yeah, great. I think all set then. If you face any challenge, we'll come back again. Right. So let's get started quickly. Now, so let's. So today's agenda. What is today's agenda? In very quick. In today we are going to see, that we are going to take a text, okay, and we will see now this text, we cannot directly feed into an LLM, right? There has to be something in between. Just like, your program in C language cannot directly run by your operating system. It has to be translated into assembly language somehow, and that only it can understand. In the same way, what LLM actually understand is a vector, basically the series of numbers. A vector, I would say, is a series of numbers. And so this is kind of a instruction set, or I would say both instruction set and data for LLMs. Okay, but what we have today is a text, which is not a number, which is a text, right? So how to go about converting this text into this vector, a series of vectors, like every word will be converted into, not character by the way, word, or maybe a part of the word, we will talk about it later, will be converted into a vector. And this vector is very special vector actually. It also, not only it designate that word, but also in a way it also understand the meaning of the word. Okay, and not only meaning of the word, it also understand the meaning of the word in the context of this whole sentence. Okay, for example, yeah, I will say financial. I store my money in a financial bank versus I go to picnic on a river bank. Right here, the bank word, the meaning of bank word is quite different in these two sentences. Correct, although it is same. So how to understand the bank meaning from the context? This is what, this those the whole beauty of this algorithm is, that we will understand in subsequent sections. Right, today by the way we will just focus on converting it into very near to this embedding, but we call it tokenized IDs, numbers, which we can convert back to then embeddings later on. Okay, so this is a part and which is very important. Now, just give you a background, for the last, all of you must be knowing, natural language processing is not new. It has been there for at least 3 4 decades now. Okay, and just want to touch upon a small difference between what natural language processing was before and what has changed in LLM. LLM is also a natural language processing models. it it can process natural language, the language we speak. So earlier the process was little complex, like training documents. Then it used to split the words, sentences into words. It used to then remove spatial characters, which is a starking difference between today and yesterday, 1.0 and LLMs. It used to, remove lower case. It used to kind of convert this into just lower cases, punctuations, URLs, HTML tags. It used to remove a lot of things. And then it used to do something called transformations. It used to simplify words, such as if you say studies, then it will be converted into either a study with Y or just I, which is a base word. Stem, we call it a stem, like in a tree, we have base, right? In the same way. It used to remove certain things from as a suffix and used to convert it. Okay. Then there is also a process called lemmatization, which means various words will be converted into one word, which is which understand the meaning of various other words, right? Like analogies and all those stuff. The reason for all of this was that to simplify the task of machine learning, because machine, if we keep all these spatial characters and everything and various varieties of words, then your machine learning models was used to perform, not used to perform up to the mark. So what was done is convert the text into and simplify the text. The problem with this is that it was good at classification tasks, such as classifying whether word is negative, positive, the sentence or paragraph is negative in sentiment or positive in sentiment. But it cannot do a lot of things, like it cannot generate text, number one. And it used to cannot even summarize text, or cannot even convert text into another. The translation part was not happening earlier, not to a good extent, because it used to lose a lot of information while doing this translation, right? So that was natural language processing 1.0. Now what has changed in this LLM, the LLM also does natural language processing, is that it has actually removed all of these area, process substeps. It removed, it doesn't actually, it has a way, it considers everything. Okay, so it removed, this part, even stemming also is removed in a way, but then it uses it for another reason. But in a way, it has also removed stemming, because it need to understand studying versus studied versus, like all these past, present, perfect tense, etc. It need to know that in order to generate words, right? Just like we do, if the grammar is not correct, then there can be many meanings and we cannot read it properly. And this whole process, then we can club it as tokenization. Okay, the process of tokenization is that you take training documents and then convert it into something that can be used for training, which is actually nothing but vectors, which we study, like numbers. It convert the whole text into numbers, a series of numbers. Okay, so that is a difference, a quite, and the difference actually has a excellent side effect, that in this way we can retain all the information of the text while training the models. However, the model has to be enough powerful, right? Therefore you see large language models, because they need to understand a lot of things and they need to be very large too. Earlier, and therefore, we have to train them for millions of dollars, to understand the whole meaning of the sentences, right? Any questions? Let me know. So I hope you understood the difference between NLP 1.0 and 2.0. Of course, it is very short, but just to want, yeah, yeah, just give a thumbs up if you are okay. Yeah, great. Yeah. All right. Thank you. Now let's go back. Now let's start building stuff. Okay. And what I'm going to do is I'm going to switch between theory and some bit of practical thing also, so that you get maximum output from this session. So let's start with tokenization. So what is tokenization? Okay, and how does tokenization work? So as previously explained, tokenization is a process of converting text into numbers. Okay, and these numbers then will be converted into embeddings that we will cover later on. Okay, and how this is really done. Uh, so consider that I have first, in order to build LLMs, I need to collect documents. Now, generally LLMs, collect these documents from the internet, right? From internet media companies, they crawl the whole internet, and I think GPT is trained on, say, 5% of the whole internet data, right? It is crawled from various places, code, text, books, everything. Okay, and these docs are nothing but text or code. Code is also in a way text, right? Of this kind. GenAI is awesome. Let's learn. Okay, and there's a series of this thing. Then this text is then split into something. Then you can split this text by, say, a space or spatial or some characters we will have, by which we will split it into words, something like this. Now, and these words are called tokens. So when we say, when I in the beginning I said tokens, I think this is what we are talking about, tokens. So these are the actually tokens. Okay, and how these tokens are created, we will look it in the hands-on section too. Okay, so very simplistically, you can just split it by spaces, very simple, but then it won't work in many cases. Uh, if it is a source code, for example, code generation need to split from various other ways. Okay, so first split it like this, tuck tuck tuck, and then you assign a unique number. So imagine that this is a huge internet. We have crawled the text from all internet, so we assume that you have got all possible words in your library now, and a lot of these words will be repeated, right? And these words will have various degree of varieties, like all the past tense, present tense, names of the world, names of the countries, people names, concept names. Even my tutorial will be, if it were part of the training set, then whatever I'm saying, this everything will become part of their library, vocabulary. Yeah. So we can assume now that now we are ready to build a vocabulary of everything, every word, every concept possible in this whole world, even the names of presidents, everything. Okay, even the code, the code, any token which is used in the code, everything, right? Of course, while creating this training set, generally it's a good practice to remove sensitive information, BIIs, malicious information, so on. Okay, then for each token, or I'll not call it a word for a reason, so I'll call it a token now, very similar to word, but actually it is not, because even the dot in this case will also be considered as token. It's not removed, it's considered. Even the Okay, therefore I will call it a token, and each token then is assigned a unique number, and this number assignment can be actually random. It's nothing. In this case, the assigning of number to token can be anything. The only requirement is every token should have a unique number. Okay, and after that, for some I think you will see, we will see in the later on, that we also need some spatial tokens. I think while playing with LLMs, you might have seen that they have some spatial tokens for end of statement, beginning of the document, end of the document, and so on. So we can also add some spatial tokens at the end of this vocabulary. So this will, okay, so this is a vocabulary, it's a map between token and numbers. And these numbers, and every token should get a unique ID. Okay. Now the question you may ask is, how do you append text from multiple documents, right? Sorry, this is documents. So if I have, say, 1 million document, will I just append them as it is, or will I have a demarcation? Okay, this is the text from this document, this is a text from this document, and so on. So we will see that there is a spatial token which is used to kind of demarcate the text from various documents, so that LLM knows that it is this document, this information is coming from a different source, rather than the same source. Okay. How do you handle unknown words or symbols not in the vocabulary? Now consider a case like, whatever we do, there will always be some tokens or words that this vocabulary will miss out. For example, I can always create a unique UUID or unique API key or unique name which no one has seen before. What's going to happen? How this should be handled by this tokenization process. So we will see, there are two approaches we will see in the future, right? And then how do we convert text into tokens like IDs and numbers? So this is what we are going to see, I think, in the subsequent slides and sections. Okay. So very quickly, to answer your first question, how do tokens from multiple documents are create are so basically the our goal right now is to create a training text corpus, and this is a huge text combined together by appending text from all the documents. Okay, that's the goal. And while combining together, what we do is we take a spatial token. So this end of text, this is actually a token. Okay, it's a spatial, we call it a spatial token, we use it to demarcate the text coming from multiple tokens. Like the first document will go there, then this spatial token, then this document, then this spatial token, then this document, and so on. Now consider how large will this text be when you consider the internet-wide data, which is terabytes of data. Okay. Of course, this won't be in a single file. It will be a very large file system. You will store it. But this is the primarily the process you will have. And okay. Now, second question we will answer is how will you handle unknown words? Okay. So what can be the way? I think logically one way is that for every unknown word encounter, I will use a spatial token to kind of whenever unknown word is specified, I will use a spatial token called UNK this to specify that this is a new token I have not seen before. But the drawback of this is that in the output, because in the output also LLM will start generating these unknown tokens, key spatial words. Okay, and if you have used ChatGPT, it has not done it so far, right? It might have done it, might used to do it in the past, but not right now. The reason is it uses another technique, and this technique is called byte pair encoding. Here the idea is that you will break the word for any unknown things you have seen before. You will start, suppose it finds an unknown word or something it has not seen before, then it will start breaking it up and map it into known words that it has seen in the past. Okay, for example, this is the unknown thing it has never seen before, so it will start breaking it up and say, okay, AK, it will start A and then K. If AK is in our vocabulary, it will map it to AK. WI, it will map it to W. IR, it will map it to IR. W again to W. Space, and IER, it might have in its vocabulary, so it will map it to 959. Okay, so this is what it does. This is called byte pair encoding, and it is the encoding basically is the process of tokenizing your text, to convert it into tokens. It is used by latest, GPT-2 to GPT-3. GPT-4 may have now some advanced version, but it was quite popular up to GPT-3. Okay. Yeah. So now what we are going to do is we are going to do some hands-on. Yeah. So this is good enough as a background. Now what you can do is you can go to, we will see whatever we have discussed so far. Now we are going to do it, okay, for us. Now we'll go a little slow also so that you can get started. For those who just joined, what you can do is you can open this notebook. I'm pinging it again, okay, and open it in your Kaggle account, okay, and and for again those who have just joined, I think what you can do is you can join this WhatsApp group in case we need to share and coordinate in the future or even right now. You can just go to your WhatsApp and scan this image. Okay. All right. So let's go to our. I'll also let's go to our Kaggle notebook and see um, how can we get started. Just one moment. Yeah. All right. Now, okay, so go to your Kaggle notebook. When you open that link, you have to say copy and edit. Okay. Now, if you are here, one thing you can do is you can start a session. Okay. You can go to accelerate. I think you don't need a GPU today, but we will need it when we train. So start a session here. So once you start, it will open up a session. Okay. And after some time, you will see, that it is running a CPU. Now we will start with data processing. Okay, and what are we going to do is load the corpus of text. Yeah, yeah. So click here, click here. Yeah, 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 yeah. And just check before even starting the notebook on your this there is a button here. Just click here. Yeah. Then there will be session options, and make sure you have this internet on. Just check if it is on. Yeah. Is it on? Just click here. Yeah. I think I took a lot of time, debugging this, so I would want to. Yeah, yeah. Just yeah, this one. Yeah, yeah. Is it on for you? No? Ah, but not that. Okay, okay, okay. Then you need to actually sign up with a mobile number. Looks like. Is there a option there saying that sign up, register your mobile number or something? Yeah, yeah. Do that. Do that. Okay. Otherwise, you won't be able to download few things. Like this is what we need. This is what we need. Kaggle.com is okay. The reason we are using this is that it's by Google. It is one of the most popular platform for learning machine learning, for machine learning, and it provides a lot of free resources like this. Even if you need as GPUs, for example, in the future, we can have some GPUs available for free. Okay, so that is the reason, and it is online. We don't need a shell. You can also run this in a shell, by the way, in your local environment. Just copy paste and you can do it on your local environment too if you have Python installed. Okay. Yeah, 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 no problem, do it. It will take. Yeah, it will. Yeah, yeah, yeah. Okay, we can maybe just we can come back once you are done. We can again come back, right? So let me quickly walk through this and then we can come back. So in this session now, for others, are you ready? Just say thumbs ups because just want to be this part. Actually we need to be on sync at least for some time, and then you can take your course, not a challenge. Yeah, one thumbs up. Great. Then I think let me know if anyone wants anything right now, then I'll start. I'll jump to the Kaggle notebook. I won't be able to see it here anything. So okay, so I assume you are all set. So let's get started. Okay, so once your session is on like this, what you do is you first, I think what we need is we need to load the data. Okay, so there is a link provided here. I added this link yesterday, in for this session, and this is actually a book, a very famous book for all of the cybersecurity professionals, like us. We'll come to know what this book is later on. It's just for this training, by the way, not for publishing it. Okay, uh, so what you can do is, let's get started. The first thing you need to do is to install PDF, how to read the PDF document. So there is a, uh, even I'm facing challenge. 1 minute. Somehow, okay, I'll again load it. Somehow it's not loading it. You can just refresh it if it doesn't work. Best way. And I hope, uh, all right. So what you can do is, you can just click it here, pip install. Okay, when you click run pip install, it will install this by PDF. Then we will download this document. This is a PDF file, of a book. It will be downloaded locally. Now what you can do is, one thing we will do is start writing. We will read the PDF document. So this code, actually what it does, it PDF, it opens a PDF reader, read the document, and it has few methods like reader pages. It finds a number of pages and so on. Okay. And then what we are doing is, for each page, we are extracting the text from the page and we are adding it into this array. And then we are joining all of these pages using this spatial, as I mentioned before, that in order to append multiple documents, we can use a spatial character called end of text, right? This character, and you can use this to uh, join all these pages together. Okay, so there is a raw text which will have so there are the number of pages in this document is 223, and I think the next section, if you run, it will also tell you the amount of, it's very basically still a very small corpus. I'll Rajiv, can you please mute in case you're not speaking? Yeah, yeah. Thank you. Okay. Okay, so now once you install this, then you can see the number of pages in this documents are 223, right? And then the amount of text is has is around like 484, like 4 lakh, words, or basically characters, right? Uh, so it will be words, sorry, not characters, right? Because we are possibly splitting it into length of raw text. How are we doing it? We are extracting this, and then for each page we will have length of this, so number of characters, right? Like 4 lakh 86, not very large, by the way. So this part, actually, we have just read the book, this whole book, and you can guess the name of the book is Hacking the Art of Exploitation. Yeah, the reason I chose this book, because it has a lot of spatial characters. It also has code, it has assembly language, shell code, a lot of things which which LLMs may find difficult. So that we may have to explain you the examples. Yeah, can you share the link or PDF? Okay, link or PDF. So uh, for PDF. Okay, okay. So this is the link. If you are locally running it on your machine, yep. Okay. I hope, Brinda, you got it. And Rajiv, are you on track? Like, did you get OTP? No? Great. No, no, no. Okay, okay, got it. So you don't have to install anything. Just, go this section. Can you see my section? Just click this button, run. Yeah, yeah. I'm not sure, it is not giving an output. Just click the next button. It should get download, and then click this button. Yeah, even I'm not getting it. Yeah. I think even I'm not getting any log here, some challenge. So don't worry about it. What you can do, you go to the next and click this, and if it works for you, then it is installed already. Okay. Yeah, yeah, yeah. So finally, up to this point, look, what we have done is we have loaded a text, we have read its pages, and we have then appended it into a big text, which is this, okay, raw text, which is nothing but a text, basically, a text of all pages, appended by a spatial character, spatial symbol. Now, next, what are we going to do is, and what is the next step? We discussed that we will split this into words. We call them tokens, right? We call them tokens. And this is where, the magic happens. Now, if it is now this is where, the magic starts happening, because, loading the data, You can, like, if I'm training a multilingual LLM, then in this phase, I will start collecting data which is related to a different language like Telugu, Tamil. I will collect all the literatures which are available, books, everything. Even the local newspaper clip, newspaper, text, everything, and then dump it into some directory and do some fine processing, pre-processing, right? And then finally, I will be able to append it together into a big corpus of text. That's what I would have done it in order to, start training LLM on a, say I'm training LLM for Sanskrit. So what I'm going to do is I'm going to collect our all Vedas, okay, somewhere which is available online maybe, okay, and then I'm going to maybe go to north side and also find out text which are written in Sanskrit, maybe our textbooks, for example, for our languages, for our school, uh, right, and then I would have collected it, everything, and then I might have got like few GBs of data. Now here the challenge happens, like, for in order to train LLMs, few GBs may not be good enough, because LLMs need to have a lot of data, okay. This is the one challenge, while training LLMs for different base LLM for different languages, right? And then I hope, if we would have got it, then we would have simply appended it in the similar way that we have just done it. Okay. Now the next question arises: how to split it into words that will become our tokens, right? So here what we are doing is we are using a regex here, pre-processing regex. We are using a regex, uh, and then we are splitting it by some spatial characters, like split wherever you find a comma, dot, question mark, exclamation sign, this brackets, okay, dot dots, dash dash, and space. Okay, so these are the possible ways, wherever I find it, I'll split it. So once I split it, and then I will do one thing. I will also kind of strip, in the sense I will remove the white spaces, from these words. So once I do it, I think what I get is a list of words which I have got from all of this. Okay. If it were a Sanskrit, then I would have split probably by, any ideas how I would have split? By spaces, definitely. Um, any other ways? I think by the danda, we call it stick, right? By which we stop Sanskrit sentence. Maybe that would have been one. And actually, I've forgotten Sanskrit, so I don't know. But looks like not many options. Few. Poonviram. Correct, correct. Yeah, thanks. Thanks. Thanks, Rajiv. And anything else? We would have stopped Sanskrit. Words. Yeah, correct, correct, correct. Yes, yes. Excellent, excellent. Look, this is where what I was talking. But then still, maybe less complex than, this a text where you have code and everything. Correct? Like English also, you will have like maybe comma, maybe dot, exclamation. That's it, few things. But when it comes to coding, it may have a code, it may have some other characters. Then you need to have more characters to split it. Okay. And if you're not doing it properly, then what can happen, I'll tell you, is this is what can happen. Can you look at this? So what it is saying, ISBN colon and the number, and how many of these possible variety of words possible in the corpus, can you tell me? Virtually infinite, right? I can keep on generating this number as many times as I want. So is this a good token or not so good token? Yeah, correct, correct. Exactly. Look at this word, I think. This is again, combination of multiple things, and there are infinite number which is possible, right? I can keep on combining 0x 300 programming and so on. So this is not a great, tokenization. What we need to do is we need to enhance it. So what can we do is you can simply, add few things here, like say I have already seen this, right? Colon. So I can just go and add a escape character and colon again here. and then I should, if I split it again, then you can see that my tokenization is little better than before. Can you see? It has now converting into ISBN colon. Look, I don't have to lose this information. This is very important because this combined with this becomes your ISBN number. And LLM actually will learn it because they always come together. Okay. But I need to learn it like this. I need to learn that as ISBN colon and any number is an ISBN number. That's what LLM should learn. Correct. Therefore, now we have done it a little better. What about this? I think we can still do better by adding few more stuff. Like where did I add before? Yeah, maybe if I add this, let's see if it improves certain things. Yeah. So I think this is another spatial character. Looks like this is not the same thing which we have done. Let's see if it really. This is a facial character. Yeah. So in this way, can you see that it is now actually it is better than before because we have broken it into as granular as possible. Of course, not the granular, most granular, but as granular as possible. So this is how the splitting happens, and of course the actual LLMs will use very sophisticated. We will come to that sophisticated mechanism to do it. You will also notice that we are not converting things into lowercase for a reason. We are not saying small I and introduction. And the reason for this is while generation, right? While generation, these capital letters also make sense. Like when we start a sentence, you start with a capital letter. So after dot, a capital letter can come. That's what the LLM should learn from this training, right? And therefore, in NLP 1.0, this would have been like converting everything into small letters, removing all these characters. That would have been the approach, but in LLM, that is not the case. Okay, makes sense. Are you finding it useful, insightful so far? Like, are you getting? Yeah, great, great. Uh-huh. Hmm. Hmm. Yeah, yeah. We'll come to that. We'll come to that. Actually, still, it is a very naive, you know, way of breaking. I'm just explaining you how it works under the hood. But we will use a spatial library in the future cases because we don't want to build everything. Yeah. Hmm. Which one? It's broke actually. Uh, Maybe this is a spatial character. This is acha, hacking watermark. Okay, okay, okay. Hacking. Third line. Okay, this one. Okay, okay, okay. Interesting, interesting. No, no, nice. No, it is. It is. Actually, this is a different section. Different section. This is in this section I've added. Look, you have to copy that character because that is not the hyphen we have. This is a special character, some other special character. Okay, so copy that and then include it into this. Okay, yeah, it has broken actually. Can you see that it has? Yeah, great. So now we have done something better. Okay, now how to build a vocabulary. Okay, so as I said before, what you need to do is all of these unique to find out the unique words or tokens. Okay, unique. I mean, hacking appearing two times will be one only. Correct. And then find these unique words or tokens and sort them out maybe, and then assign a number from 0 to whatever number of unique tokens you have. Okay, that's what we will do to create a vocabulary, and this is what is done in this section. Okay, so we have first find out the unique words using set, then sort them out from 1 to, by the way, this is completely random. You can also assign any random order. It does not matter what integer you will assign to these tokens. This is just one of the way. Okay, and if you assign any integer, and if you are building your own LLMs, okay, then it will not matter. But okay, so this is what we do. We take all words, then we find out the vocabulary size, and then for each word we assign a token, a unique number from 0 to whatever number of. This is what this code does. So if you just look at this code, then there are, in the vocabulary we have got like 8,799 tokens, and these are the tokens. Like first 50 tokens are this. So from exclamation assign 0, this assign 1, hash assign 2, hash has 3, hash this. So these are all the possible things which we were not able to split as assigned a number. Okay, and you can see that there are few cases. I think this is a bad tokenization, because our tokenization is pretty naive. In real tokenization, I think, because this looks like to be an arbitrary string, correct, and this probably will not occur in any other places, may not occur that often. So assigning, considering that as part of your vocabulary is going to be expensive. Okay, like the number of words in a vocabulary definitely should be comprehensive, but the more number it has, the more the more computing power and the more the size of the LLM, it will increase the size of the LLM. Okay, so this is a bad way of creating vocabulary, but as we said, it is, we are going very simplistic right now. So can we do better? Yes, we will see in the future. Okay, now, so far what we have done is build a vocabulary, right, by using this. Now what next we are going to do is, I think you can skip this part. So we have done the vocabulary, and this vocabulary is stored in a vocab thing, and that we are going to use in the future. Okay, so we have created our own vocabulary and we are going to use it in the future. Now I'll just quickly implement, show you a simple tokenizer that you can go through. So a tokenizer, I think, will have two methods. Okay, one is to encode, right? So what is encode will do? It will take a text and then convert it into a series of integers. I think we saw in the presentation, right? The text was converted into series of integers. Yes, yes, yeah. Mhm. Mhm. Yes, yes, byte pair encoding. Correct. Yeah, yeah. No, no. Yeah, yeah. So currently, we are looking at our own encoding. Okay, and we will now quickly jump into byte pair encoding. We will not implement it. We will use a library, because implementing it will be complex. But I just wanted to let you guys know that how the encoding and what tricky things we have to do while encoding itself, right? Like okay, so that's what I wanted to explain. Yeah. Hmm. Hmm. Yeah, yeah, yeah. That yes, that's correct. That's correct. That's correct. That's something. So we will jump to that actually very quickly. Okay, right. Now, what next section I like to, as I like to kind of do little bit of jumping, and you can, what this sections will do is it will just implement few methods like encoding, decoding, which is very similar to any tokenizer you're going to use. Like if you go to Hugging Face and use a model, you might have seen that it also gives you a tokenizer, and that tokenizer, you use it to convert a text into tokens and converting back from tokens into text, right? So under the hood, this is how this is what it is going to do, right? What we have seen already, it is going to take a text, split it, and then use a vocabulary to convert it into integers while encoding. So encoding means text to integers, and decoding will be just reverse. You take a series of numbers and you convert it into a text. Okay, so these are the two things that it does. So we will not go in detail, otherwise we will skip our time. What I want to just show a quick example that this is what encode will do. It convert text into numbers, and the decode will convert back into the numbers again. Okay, and next thing what I'm going to show is that if this encoder finds a word which is not there in the library, it is going to break unless we handle it right. So like this code will not work because some of the words will not be in the library, like this Gisberg, painted. I think in art of exploitation there is no mention of painting. Right, a lot of hacking but no painting. We would have taken a book called Hackers and Painters, then I think both would have been there. So unfortunately there is no painting in this book. So our tokenizer is failing. We can handle this by using special characters, but I think the best thing now we can do is we can use a library called tick token. Okay, so go to the next section. I think there is something called byte pair encoding, and this is a bit more advanced than what we have seen, what we have implemented so far. But under the hood, it is just a complex version of what we have done. Right now, we know how it's happening. Just splitting into words, use a vocabulary, write a class where it can convert text into integers and integers into text. Okay, and use some spatial tokens whenever no text is found out. So are you on this section? Please scroll down and come to tick token. Tick token. So this is a library I think is built by OpenAI, is released by OpenAI themselves. It is much more faster as per OpenAI, than the tokenization library released by Hugging Face. So if you go to their GitHub site, you will get to know what is the difference. Okay, and this is called byte pair encoding for a reason, because it handles even the unknown words or tokens found in the input, like while inferencing. So training is already considered, but while inferencing, if it finds a new token, it still handles it. That's the beauty of this. And as you can see that it is, as per them, it is much more faster than Hugging Face, right? What Hugging Face has defined. And so what we are going to do is quickly install it. And, yeah. Hmm. Yeah. Yes, yes, yes. Hugging Face. Now, this is a good question. Hugging Face, if you just go to Tokenizer, they will be having, few tutorials and everything. But their tutorial is more about how to use their tokenizer. Okay. So now you will be in the good position to read this. You will understand a lot of things. Okay. Yeah. So maybe after this great idea, just go ahead. I think this is not tutorial. Somewhere they will have like text models. Somewhere they will have. Just go to tutorials. You will get it. Tutorials is there. Preprocesses data. Yeah. Okay. So you can see the text use a tokenizer to convert text into sequence of tokens. Yeah. And this is the tokenizer class. Okay. Maybe at some point we can cover that also, but not today. Today we will focus on our stuff. So TikToken is to installed. Now we will actually just quickly explore what is the difference so that you understand. So this is just to print the version. Now TikToken, supports multiple encodings like GPT-2, GPT-3, and so on. Okay, so like now when I say encoding, it means this is how GPT-2, which is OpenAI AI's earliest model. Look, all of these models, this is very important. Now you can understand vocabulary. When we talk about vocabulary, you can assume that when a new model is released, like GPT 4.0, which is the latest version, or even Gemini Turbo, which is their latest version, they try to make the model more powerful, correct? How can they make it more powerful? The first simplest way is to add more vocabulary, to add a lot of other items into vocabulary. Okay, change the vocabulary so that it understands and optimize the book. Sometimes it is not just increasing the vocabulary, sometimes it is all about optimizing the vocabulary. For example, earlier GPT-2 was not able to handle Python code, because Python code, what happens, even the indentation matters. Like if I just give a space here and I try to run, it gives an error. Okay, so can you believe that? how how can a model generate a code if it does not really care about, and it has to exactly give code with proper indentation, otherwise not going to work. Okay, so how all of this can be learned by OpenAI, or all of these models, right? The one of the ways to actually now split in a various ways, like also consider not just one space but multiple spaces together, two or three or four spaces together, so that it can learn key in a right, it can learn that there is a tab required. Okay, right, so this is how it is done. So what we are doing here is we are telling it to load GPT-2 encoding, okay, which is very basic but still very powerful. Yeah, so when we click, it loads a tokenizer with GPT-2 encoding. Okay, and this tokenizer has the same methods as we saw earlier, which is simple tokenizer we saw earlier, right? This encode decode, it has a similar thing, same method. So now let us see what we are going to do. So this is how you can use it. You just give a text. This can be this text, and it also has a spatial you know parameter where you can say this is my spatial token you need to consider. So suppose you have multiple documents, you want to attach them together using a spatial token like this end of text token. Then you need to enable this flag, okay, allowed spatial token, and you can give a list maybe, right? Okay, list of these tokens. So you can specify your spatial tokens, okay? And then what it does, it simply, convert it into a text into integers. And given an integers, you can also decode it back. And what happens is now you take these integers and give them to LLM. Now you train and give them to LLM, right? Give to LLM. LLM gives LLM generates integers, these integers as the output, int as output, sequence of integers as output, and you can take this output and again decode back to strings. So this is how you do it. Okay, so encode, you can either do training or just run LLM and generate the text and take the, actually it does not, LLM does not generate text, it generates integers. You again take the integer and decode it back to strings, your string, original string. Okay, now let's see how this, no, let's see some of the interesting things about tick tokenizer. Okay, and this is where interesting things will happen. Now you will understand how can you even save cost if you're building on top of LLM. Yeah. So let's get started. Say I have this text where I have noted, I have added like doing, done, took, take, some keywords I have added. Okay, and let's see what tick token will do with this. So this is a text, and it has like 1, 2, 3, 4, 5, 6, 7 words separated by spaces, right? And these 7 words actually got converted into 16 tokens. Okay, 16 token, and each token is a number. So I will assume 32 bytes, correct? 32 or 64 maybe. I assume it is 32 bytes. Actually, it may not be 32, but because number of tokens, vocabulary size will be not more than say 54,000 or 64,000. Then I think you can 1 2 bytes should be good enough. Depends on what kind of uh, what is the vocabulary size. So you can use certain words, number of Okay. Uh, so as you can see that this text of certain length, I think this is definitely more than certain like 50, 60 characters, right? It is converted into 16 tokens. However, and while converting, can you see that it is breaking this into this, like it is breaking doing into do and ing separately. Stemming, we discussed stemming, correct? That stemming is breaking the stem, but it is not throwing ing, it is still keeping it in a sequence, but still it is converting into two different words, because now what will happen, its vocabulary size will decrease. Rather than storing doing, done and everything, doing and do, two at least words in the vocabulary, it can actually store do, and ing will be common for a lot of words. So it is in this way reducing the size of the vocabulary. Okay, so this is why it this token library kind of split uses stemming in a way to break things, so that it can first of all reduce the size of the vocabulary, but at the same time it can actually handle even unknown words. So I'll show you how. Say, okay, so this is one thing you have noticed, that it is kind of breaking things, okay, using stemming. Second thing, you can notice that suppose this is a string which is a random string, correct? Of course this will not be there in the vocabulary. So how is this tokenizer going to handle this? Do you think it will fail, or do you think something will happen? Any guesses? What's it going to do? Yeah. So this is where this name suggests. I think this name, byte pair encoding, BPE, this is where it comes from. That even if there is a random string like this, it can handle it in this way. So you can see that this string is actually get converted into pair of characters most of the time. Not sometime no, but most of the time, right? Like 78, 94, 75, 89, 47, and then maybe it has 508 in the vocabulary for some reason. So it has mapped it to 508, 495, but again 70 for 75. So what it does actually, it takes all the characters and numbers, and it also store the pair of all the combination, two a pair of these combinations in the vocabulary. In this way it can handle any arbitrary number or string, right? Okay, makes sense. Okay, so now you can see that first, so you saw that this library can this approach by BPE, byte pair encoding, can handle any arbitrary string, even not in the vocabulary in this way. But then there is another thing you should notice, that okay, this is my, say, a random number. It can be an API key, correct? Ideally, and then what it is costing me, how many tokens is it costing me? Can you see that it is costing me 21 tokens, right? So if you have a data which has a lot of random numbers, and even the URLs like this, I'll show you, even in this case it will have, right? Then you can imagine you are using more number of tokens from LLMs. Your queries will be little more expensive in terms of LLMs when LLM handles, because these random things will be converted into small, bits, pairs. It will be sent to LLM. LLM will process it and again give back the output and so on, right? Even by generation itself, it will emit multiple tokens, tuck, 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 right? So this is where you can do some optimization when you are using LLMs. You can kind of convert it into maybe some token which is known, which is well known, or a spatial token, spatial character token, a smaller token, maybe just maybe colon API key. That's it, done, right? And what will happen now, that you can reduce the number of tokens either for processing or for even output. The same case happens with URLs. So if you go to URLs, you can see that it is using 29 tokens. But does LLM need to really understand this URL? If it no, then you can simply replace it with the with a keyword called URL or something, that you can replace later on, or URL 123 like this, and then it will reduce the number of tokens from 29 to just 2. Okay, URL and then 1 maybe, right? URL, like if I just have URL, understood? Any questions? So while using LLM, I think you can actually optimize your things to good extent in case your purpose is really spatial. Like I want to just show you what URL1 will look like. So you can see that it is just using 2 tokens, right? URL and 1. So we have reduced from 20 tokens to 2 tokens, like 10x already improvement possible, right? In this case, at least. Okay, so while you are using LLMs, I think you can also pay attention to how your tokens are being created, because whatever text you are giving it to the LLM. What is raw text? So, raw text is okay. Sorry, I didn't saw your question. Raw text, I think we have defined previously in this slide. Okay, so you can pay attention to your tokens. Now, I will not go into this. You can also run it and see yourself how a code like this will be taken care of. This will be handled by the way, tick token. Okay. Now, next thing which I want to quickly show is how this, now we have converted text into tokens, right? Tokens are integers, but are we there for training? Do we need to do anything else for training the LLMs? This is where, we need to do one more thing that I'll just quickly cover and then we will end. Okay, so we have done up to this, we have done up to this. Now we will understand few more concepts. Okay, I think we have less time, so we may kind of finish quickly and also give you an exercise maybe, right? So we will just understand few things like what is an LLM? I think everyone knows LLM generate text, but how does it really generate text? Okay, so what under the hood, I think most of you know now that LLM just predicts the next word given the previous words it has seen. So for example, in this case, if my input word was LLMs learn, then if you give it to LLM, it might actually first produce 2. Then it will see these 3 words. Based on these 3 words, the next word it is going to predict itself. Then going to see again these 4 words and again going to predict 1 and so on. So this is how every LLM will work. It will keep on predicting the next word based on the previous known words it has either taken as an input and also produced so far. Okay, so these are 2 things taken as an input, and then it starts producing, and it also consider that also as the input again and start predicting the next word. This is interesting, right? And using just this simple process, actually it can do such amazing thing what ChatGPT, what Gemini and other LLMs are doing. Okay, so now in this process there are few interesting things you should notice. Number one is how many, like if you just keep the LLM going like this, what do you think how many tokens it should produce, and how to control it? Okay, so that is controlled by something called max tokens. Okay, the max token and max length, 2 parameters. So what max token does it that it tells LLM how many maximum tokens it can produce, and before that it has to stop. Okay, so in this way you can actually limit the, otherwise LLMs can keep going forever. Like it can, after some time it will start hallucinating and it will just hallucinate for eternity, right? That does not happen, by the way. The reason is there is a parameter called max token which defines how many maximum tokens it can produce, but it can always finish before those max tokens. Okay, and when, and how does it know? I think this is where, when to stop. It is taken care by the our spatial symbol we have seen before, end of text. So what happens that LLM start producing next word, and whenever it encounters end of text, symbol, it knows that it need to stop, and somehow it produce that end of text symbol somehow, during this training and everything. It is trained to produce this end of text where it thinks it has given the answer. Okay, so this is the magic that happens, and how it happens we will learn maybe over a period of time, but this is how it happens. Okay. Second thing, you might have heard, that LLM, LLM has certain context window, and nowadays all vendors want to increase their context window. So what is this context window? Okay, for example, Google Gemini has a context window of 100K tokens, which means it can see up to 100K tokens for predicting the next word, which is very interesting, right? That you can give a maybe few chapters of a book, it can still remember the whole chapters of the book to predict the next token, which is amazing. I mean, in terms of code, you can see 100K code it can see and still produce the next token. Amazing, right? Yeah. Context, length, context window are both same. Yeah. It's a length of the window. Yeah. Yeah. Okay. Right. Context window understood that it's the amount of words it it will hold in its memory to produce the next token. This is what it is. It's basically like how many words can you remember in your head. This is the same thing in terms of token, in terms of LLM. They also have something called working RAM. That's what we have. Okay, and the bigger the token, the bigger the LLM, it can have more context window. That's what is happening nowadays. And like Llama 3 has a context window of around 8K, okay, which is not that big. By the way, there is a very good site I can show where you can compare all these LLMs. I'll just quickly ping it into, okay. If you look at this site, I think you get to realize, okay, you can open it and you get to see, some of the things like you can go to models and just look at say llama or any you open any model and then you will get to know there is something called context window has okay, and its context window is 8.2K tokens, which means it can see up to 8.2K tokens max to predict the next token. Okay, and different models have different context window, like GPT-4 probably have larger. You can see it is 130K tokens, which is very good. Yeah, Gemini, Gemini Turbo. Okay, Gemini 3. Pro. Let's see what Gemini has. Look at this Gemini context window. They claim they have around 1.5 million, 1.0 million length of window, which is huge, 10x more than GPT. They claim it. Okay, at least. So now you understand what is context window, and we are going to use it, by the way. There is another thing which is called training batch, okay, where we will not give like one example at a time for training, but a batch of examples. Okay, so that's what it is. Now, many of you might have already, done some machine learning. Okay, may not be LLM, maybe LLM, and you may already know that in order to train a machine learning model, what you need to give in a training, an example input and example output. You need to collect all these example input output and give it to the model and it can train. In the case of LLM, what can be this X and Y? Like what can be your input, what can be your output? It has to be in your text, right? The text that you have collected so far. So as we have seen before in this example, look what it is doing. It is seeing LLM learns and it is predicting 2 as an output. Okay. So what is the input? What is X here and what is Y? Consider that your context window is just two length, two tokens. What can be X and Y? So your X can be at LLM learns can be your X and your Y can be learns 2 can be your Y, correct? like when a token gets this and this, it need to produce this and this. Basically need to produce 2, but I can take learns and 2 as a y. Okay. In this case, if your x can be learn 2 can be your x, then your y can be 2 and predict. Right? So what we need to do is we need to create this x and y from the text itself. That's it. I think if we can do this, that's it. We are all done for training, at least start training an LLM. And this is not a difficult task, by the way. This is just, sliding, some kind of sliding mechanism we need, which will, of a context length, which will take this tokens as x, and from this, like if one word at a time is your x, then word at a time will be your y. That's it. I think this is what we need, a simple way. And you just keep on sliding this window and generating your x and y. That's it. And this will generate your training set. Right? LLM learns to predict. So this can be your x, this can be your y, and this become your training examples. In this case, context length is just 2 tokens, but now imagine in Gemini's case, they have to consider 1 million length of x, okay, and 1 million length of y, correct? And they have to kind of slide this window for a long time. They need to train the model in a huge amount of time, right? Okay, so quickly, I think what I can just show you that offline probably you can go and just implement this algorithm, and some example is already given. Right, so simple, just again load the tokenizer. This we have already done. Now you convert raw text into tokens. Okay, so we use tokenizer to convert raw text into tokens. This is a text we have seen, characters only. And then we will do something very simple, but then we will implement a sliding algorithm later, which is like, say, I'll take only the first from, so I will take context window of 4. Then my x will be from 0 to that context window is my x, and my y will be just one token apart from 1 to context size plus 1 become my y. So it becomes like fx and fy. And if we just run it, I think uh, we have to do this, this, and then this. Okay, so you can see that my context x is first these tokens, and y will start from this and then the next token which will be there. And these tokens are integers, right? We have already converted into integers. That's it, I think. And if we just do this in a sliding window, I think this class will do it. Then finally, what we get is a huge training set, which we are going to use for training, I think. Okay. Maybe you can go through this offline, but this is what it is doing. Look, this is where we are going to create X, a batch. By the way, here, I just want to explain that we discuss about batch. Here we are using a batch of size 4, but it can be more in real life scenarios. We are using a context length. Okay, context length of size, in this case, it will be max. I think it's called max length. Okay, it's not, this is the context length of 256. Now there is something called stride. Stride is actually like a hopping. Like when you slide, rather than sliding 111, you can slide like this much, and then after 128, next x starts. Okay, something like this. Sliding can happen continuously or in hopping way, because otherwise you will have lot of data, right? So you need to kind of stop this. Uh, so stride is another parameter. Okay, that's it. I think if you do this, then what we get is, this is the set of x. You can see that 395430, then the corresponding y starts from 5430, 25, 383, and 3683, right? 383, 383 is here. 3683, where is it now? Next, it is here in the next X. So X is shifting like 111, and Y is also shifting like 111, something like this, right? And if you do this, this becomes your training example. So this, in this process, what we have got is a training examples which we can use for training. So that we will check in the next slide, in the next section. Yeah, for some exercises for you, I think at the end you can go through this. You can change the URL, like at the start of this playbook, or there is a URL, a document I'm using. You can add your own document somewhere, find it on the internet and start the whole process again and see if it works and how do you get it. Okay, and go through the whole process again. Okay. Second, you can also, use tick token to kind of convert a code into a token and see what happens. So you can take this string, this whole string, and go to this tick token place. Like you replace this with this code and see how it is tokenizing the Python code. Okay, right? It will be interesting to know how does it take care of indentation and everything. Does it lose that information, or it actually somehow maintain the indentation into the information itself? Okay. Yeah, that's it, I think, for today. Today we covered, I believe, the heart of or one of the most important part of LLMs, and that is tokenization. And also we covered how to create training data set given a text. Okay, of course it was, and then we also learned the concept of context length, batch size, and so on. Yeah, so hi Malik. So I think we have, by the way, there are few things before we move on. One is, if you join this WhatsApp group, then I will be able to share even the information after this class and after this session, and also any other session that we are going to use. I think we can use this group to just keep coordinating. That's number one. Number two is, you can actually open this notebook. Where is it? I think I have already shared a notebook which you can, from where you can get this link. So this is the notebook. You can either do copy this, and there will be a PDF link which will be there. If you are asking the PDF, then this is the PDF link, but this link is already there in the notebook. Yeah, I've already shared on the chat section. And that's it, I think. Thanks a lot. It was good. Any questions? I will be happy to take any questions. And soon, actually, we will be going to learn about self-attention. So what we have learned so far is the tokenization, right? We have just learned how to convert text into tokens, which is nothing but numbers. Now, but LLMs are powerful because of one thing, and that is self-attention or attention. You might have already heard. So I think this is going to be a great, you know, session where we can learn what this attention is and how does really LLM understand all of this and does all of this. So this will, this is the foundation of all LLM. Okay, that we're going to do probably in the next couple of sessions. I think one is on next week, and I think I will either repeat the same thing on 27th of June. Yeah. Okay. All right. Any questions? Anything you want to share? Please go ahead. Yeah. We are a bit late, but yeah. Sure. I think, mhm, mhm. Sure, sure. I think best practices while developing LLM. Uh-huh. Sure, sure. I'll do that. I think yeah, yeah. You can either I think you look at I'll share it with you, yeah. Are you on that group maybe? Then I'll share it in the group itself or whatever. Yeah, yeah. Sure, sure. That will be great. I think if you just want to know, just go to OS top 10 LLM apps that you already know. Got it. Mm-hmm. Mm-hmm. Got it, got it, got it. I think one thing which I'm not sure whether it really map or not. I gave a session last time. You can have a look at this. Or let me think, let me, there are many documents actually. There are many documents. Maybe I'll definitely send it to you. Like CSA, for example. There are many groups, you know already. CSA, Cloud Security Alliance, has some, they're coming up with some framework to build secure LLMs and also to build secure GenAI apps, right? If you're looking for tools that you can use to conduct testing and everything, then there are some tools available. Okay, you can do that. But of course, things are evolving right now because we also are in cybersecurity space. There are tools available, but they're not in great numbers. Like Burp Suit, for example, if you want to test an application using Burp Suit, then I do not know. Isake, you are there. Maybe you may know it. That does Burp Suit support fuzzing of LLM-based APIs? Not sure. What Burp GPT does? I've not checked it, but let's. Uh, mhm. No, actually, what it does, it leverages it leverages Gen AI models to test regular traditional web apps. What I'm talking about is testing the Gen AI web apps itself. Yeah, 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 yeah. There is a exactly. Yeah, that's what I was saying. There was an app we released just to show that it is a healthcare app, and if you want, you can have a look at it. Uh, okay. What Garrick, yes, yes, Garrick is there. Yeah, yeah, exactly. Garrick is there. Then we also have our own tool. Okay, if you want to see that, you can go to this. By the way, we also have like go to dedoxioai.ai and API docs, and there you will get quick start. So it's open source tool. I think you can also have a look. Okay, yeah. And Garrick is there. Yes, Garrick. It does something very similar to what Garrick does, but in a different way. What Garrick does, it actually download all the models on your local system, correct? And perform testing of the models. Okay, like what it does, start, list probes, yeah, and it leverages other models like OpenAI to generate test cases. Okay, I think in a similar way, what our tool does, it does not, it uses our database, maybe the backend, to conduct testing of model itself. Similar, I think similar, but we have some different. We have a lot of differences from them. Yeah, yeah. It is open source. Yeah, you can just quickly have a look. If you need anything, let me know. Yeah, interesting. Yeah, so I'm pinging it.